We're talking about concavity and the second derivative test. So we can use the second derivative to find out more about maximums and minimums, but also where a function is concave up or down, or concave and convex, depending on the book you're reading. Derivative test. Okay. So let's start with basic parabola just because it's easy, and then we'll move on to some higher powered functions. Okay. So the question is determine, and I'll explain in a minute what concavity means, but let me show you how to do it first, and then I'll show you visually what it means. Determine the intervals when f of x is concave up or concave down. So step one. First thing you gotta do is find the critical numbers, just like before with the first derivative test. Find the all right. So we've done this a few times, right? We take the derivative and we set it to 0. I'm just gonna skip to there. Solve for x. X would be well, let me write it prettier. Set it to 0. X would be 1. All right, so that's step 1. Step 2 is find the second derivative. So do you agree that the second derivative would be 2, right?
Yes, sir.
Yes, sir.
So here's some notes. So since the second derivative is always positive for any x, then it is always concave up for all x. That's a little redundant. I just want to make sure, make the point. So basically, here's a easy way to remember. If you get a positive on your second derivative when you plug in a number, then that means concave up. So I can move this a little bit. So if the second derivative for some x is greater than 0, concave up. If it's negative for some x, if the second derivative is less than 0, concave down. Okay. So basically the graph would be opening downward or upward, depending on the sign of the second derivative. Okay. So if we have concave up at a critical number, that will also tell us that we have a minimum, right? If you have concave down at a critical number, then that's a maximum. So that's where we're going to use the second derivative in just a moment. Oh, I didn't answer the question though. Since it's positive no matter what, it's concave up on all real numbers. Okay. Which is obvious, right? If you graph it, what kind of graph is this?
This is a parabolic graph. Is that what you call it?
It's just a parabola, right?
Yeah, parabola.
So visually, this is what we mean. It's always concave up. It never started coming back down. So it's just always facing upward for all x, which we knew because that's what a parabola is, right? No matter what. Now, if the function like came back down, then up again, then you'd have different intervals of concavity. So on the next one, you'll see it more clearly, see what we mean by concave up and down. Okay. But you see what I mean by concave up? It's just opening upward. That's it.
Yes.
Nothing crazy. All right, so let's do a higher power function. That was just to get the main idea across. Any questions so far? Is that okay?
Yeah, okay.
Yeah, let me know at any time. Oh man, camera's messing up again. One sec. Hopefully it stays. If not, I'm gonna have to restart everything. All right, so determine the intervals for concave up or concave down. So here's a function. It's a cubic. So to find concavity, we need the critical numbers, first and second derivatives. So let's try to do stuff, multiple things at once. So in step one, let's find the first derivative and the second derivative. So that should be, right? You all agree with the first derivative?
Yes, sir.
Okay. Step two, find the inflection points. So inflection points happen when the second derivative is equal to 0. And an inflection point is when your concavity changes. So this time we're going to have a place where it's concave up and then concave down. And it shifts concavity at these points. So we find them by setting f double prime equal to 0. Looks like it's 1 again, right? All right. Step 3. Passed around the inflection point. So this will tell you where you're concave up and down. So this is the second derivative test right here. Okay, so we got 1 as my special number. And then we have, I don't know, we could pick 0, I guess. 2. Just some simple numbers. So plug these numbers into your second derivative. So negative 6 times 0 plus 6 is positive. So concave up over here. Second derivative at 2 will be negative 6 times 2 plus 6 is negative. The number doesn't matter. So concave down after the inflection point. So we can answer the question. We're concave up from negative infinity all the way into 1. Concave down after 1 until infinity. Okay, so this is what they want us to figure out. And we use a second derivative to do so. Okay. I'm going to graph it in a moment and show you how you can see it. Because the grapher makes it all super simple, but that's not the point of the exercise. But you guys are in calculus at this point. You should know at this point that the answer doesn't matter. It's not about that. Okay. At least not right now. So we had a change at 1, right? We said, what would that be? 1 comma 8. Oh shit. Here it is. So we're concave up until 1 comma 8. So that's the point of inflection where it now is concave down right afterward. Okay. You see what I mean? So change of concavity, concave up forever up until we get to this point. Now we're concave down. But visually, you can't really see it. So we need the second derivative to tell us where exactly the change happens. It's kind of hard to tell without it. But once you have it, it's pretty clear, right? You've got this part opening downward, this part opening upward. Okay. Does that make sense? Is there any questions on
No
why we
question.
have these two intervals?
I have a question.
Yeah.
So we only need 2 points for.
Yeah, because it won't change again without another inflection point. So it's going to keep being concave down or up until that.
Okay, so we only need to choose two numbers on the left and the right. So like if we have 5, then we just choose like 4 and 6.
Yeah, it doesn't matter. You choose any
Oh,
number on this either side. Doesn't matter what number you choose.
oh, okay.
But
And
if
they
you have
could
multiple
be
inflection
negative,
points, you'll choose in between all of them.
and they could be negative numbers too, right?
Yeah, it could be anything as long as it's on the left.
Oh,
Doesn't because you can see on the picture. You guys see the picture or no? Oh, maybe I never put it. Shoot, my bad. Here it is. So concave up from here to here, then right after concave down. So the inflection point, we only have one inflection point, it's right there. But you could have multiple on other functions, like higher power, like maybe 6 or 7 power or something. Then any other questions on example two?
No, I think we got it.
Okay. Let's do one more and go from there, I guess. On this one, they want us to actually find the min and max. So find all the extrema values of of the function using the second derivative test. So I prefer, well, I recommend you use the second derivative test to find max and mins unless the derivatives are a real pain. So if finding the derivative is too hard, just doing it once is good enough, then go back to the first derivative test. You know what I'm saying? So if finding a second derivative would have like multiple chain rules and products and quotients, you don't want to do it again, then this method might not be worth it. So, but if the derivative is easy, then second derivative test would be best. So this is how you use second derivative test. Step one, find the critical numbers. So let's go ahead and find the first derivative, set it to 0. Let me see. How do I write the function? Dang it. Sorry about that. We find the critical numbers of f. So first derivative will be this guy. Set this to 0. Oops. Okay, there we go. Sorry about that. So set that to 0 and get our two critical numbers.
I think you forgot the 12x squared. When you put 4x to the third minus 12x equals 0, shouldn't it be 4x to the third minus 12x squared equals 0?
Where? Here?
No, one up.
Oh, right here. Yes, I did forget the square. Yeah, I fixed it over here, but forgot over there.
Okay.
Okay. Step 2. So we got our two critical numbers. So just find the second derivative and plug them in, and that's it. So the second derivative will be 24x, right? Well, x squared, that's right. All right. Step 3, plug in the criticals, critical numbers into second derivative. Excuse me. All right. The second derivative at 0 will be 0, right? When that happens, what does that mean again?
Second derivative is a negative number.
Right. If we have if the second derivative is 0, what does that mean for this particular critical number?
That it's also 0? That there are no critical numbers?
I mean, it is critical. Remember, we said whenever the second derivative is equal to 0, it's a inflection
Oh,
point.
yeah. Inflection. Okay.
So plug in 1, we get what? A negative? Oh, actually, it should be 3. My bad. Is that 36? Yeah, I think so. So for concave up, so if we get it positive, that means we're concave up at that location. But since it's a critical, that means what? What kind of point is it?
It's a critical point.
We
Oh,
have
that's right. It's a concave
Okay.
up.
This going on. Right, we say critical numbers can be inflection points or extrema values, right?
Right.
So what type of extrema is this?
Positive.
The minimum, right?
Yeah, minimum.
The whole goal is to find a minimum using your second derivative. So we know it's going to be minimum because it's opening up, it's concave up at 3. To get the other value, you got to plug it into the original. So I did this part earlier because I don't feel like plugging that in. But you want to see it, it's this. Anyway, is there any questions on these ideas? Does it make sense?
Yes. And just so we're clear, this example doesn't have a maximum.
No, let's graph it and see what's going on. At least on a local, might have a local, might not, but
I have a question.
uh-huh.
Where it says step 3 underneath, you put F and then little lines and you put 0. And then under that you put 1, but then you plugged it into 3, not 1.
Yeah, I meant to put 3, so I changed it except right here.
Oh, okay.
I put 1 at first by accident. But thanks for letting me know. That way you can fix it. All right. Here's our graphs. So it looks like this is our inflection point. And then here's our minimum. Or concave up, then down. Interesting. It's hard to tell with the visual, but anyway, we knew we had a minimum and we knew we had an inflection point. So using the second derivative test, we were able to test the critical number. So that's all you got to do. So once you have your critical numbers, just plug them into your second derivative and you know what they are. If it's positive, then it's opening up, so it's a minimum. If it's negative, opening down, which is a maximum.
Okay.
That's why I do those happy faces so you can remember because
Oh, okay.
they're it's kind of backwards.
Okay. Now I get it.
But yeah. Plus, if it's positive, happy face, minimum. If it's negative, sad face, max. Okay. All right.
Okay.
I'll leave the rest to you. Do you have any questions on these ideas?
I have a question.
Mm-hmm.
Can we do number 5, the homework 4.4 together? I'm sure it was
4-3?
4.4,
Oh, 4-4.
question 5.
Yeah, we can.
Thank you.
Okay. This is problem 5. So here we're gonna have to do a quotient rule. gonna be funky. Oh well. Determine the open arrows. Determine the open intervals. For the graph. Raised it weird. For which the graph? Is concave up or down? Our function is right here. One moment. All right, step one. Find f prime. I'm going to rename this y so we can use those formulas or the notes we used before. Doesn't matter, just for consistency. So the derivative will be third of the top times the bottom minus derivative of the bottom times the top over bottom squared. Wow. So F is this top part. G is the bottom. So derivative of F will be 2x times G minus G prime times F over x minus 1 squared. Double checking. Yeah, we're good. Okay. I'm going to multiply all this out and then do it again. So 2x cubed minus 2x no. Minus 2x cubed. That's a weird 3. Minus 14x. This simplifies a little bit, right? These are gone. So that'll give us negative 16x over this garbage. I'll just leave it as is. So there's y prime. Let's do it again. Find y double prime. That's going to be derivative of the top, f prime, times the bottom, minus derivative of the bottom times the top. And then this will become a fourth. This is just a really gross derivative. So this would be negative 16 x squared minus 1 squared. Derivative of this will be a chain rule. So that'll be minus yeah, bring down the 2, and then times derivative of the inside, which is 2x. Then times a negative 16. I'm skipping some small derivative steps because the focus is not derivatives here. But we can talk about it after we're done if you want. Let's see. Is there any way to make this pretty? Oh wait, you could factor. All right. If I factor this out of both of these terms, I'll be left with negative 16 times x squared minus 1 minus 2 times 2 times negative 16. That'll be plus 64x squared. The derivative is done. I'm just doing algebra now for no reason. Okay. But one cool thing is I can cancel this. I couldn't resist, right? Negative 16 plus 64. What's that going to be?
That's going to be 36.
64 minus 16?
64 minus 16. I think that's 32.
Yeah, no, I don't know. I'm getting tired. Let me see.
Yeah, I'm tired too.
48, I believe.
Yeah, we're good.
Oh, it's 40. Oh,
This is as pretty as it's gonna get.
yeah, I'm tired. I'm tired.
All right. So we got our derivatives, first and second. Now they want to know where it's concave up and down. So we're gonna have to set this to 0. Oh, wait a minute. That'll be negative. positive. This should be positive, so negative, positive, negative, negative. All right, I think it's good, but I'm gonna graph it because now I'm paranoid that I made a mistake. Hmm.
I get paranoid too with these kinds of problems.
Yeah, because like if they go too far, then it's all meaningless. We need a point of concavity. Give me a moment. Actually, I think I did that, I guess. Hmm. Oh, I see. Hmm.
What happened?
No, I was overthinking it. Okay. So my issue was this numerator this will never be zero. So how do you find inflection points? But I forgot that another location that critical numbers happen is where the function is undefined. So it is undefined at I don't know that space. x plus one, x minus one. So one and negative one are two inflection points. We just gotta test around here into the second derivative. So we use this. Oh man. To plug these into the function. So test around these points. And plug them into the second derivative. So I'm going to pick 0, 2, I don't know, -2. The function again.
Is this still the same problem?
Yeah. We haven't answered the question. Okay. So we're gonna get a 16 negative, 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 negative. Concave down in between. Oops. 48 times 2 plus 16 divided by 2 squared minus 1 cubed. That's going to be positive. Who cares? Right? Uh, this would be the same thing. Positive. Don't care what the number is. So our answer should be concave up from negative infinity until -1 and after 1 till infinity. Concave down in between. Once you have the second derivative, you can test around the inflection points and you'll be good. Just remember that values that cause division by 0 can be inflection points. Anyway, any
So for
questions
that
on?
one, so for that one, we got x equals to 1 and -1.
Yeah,
Okay.
those are two inflection points.
Let me just write this down real quick. Minutes. Okay. Okay, down. Okay, I got it.
Okay. Alrighty, guys. Well, we'll stop here for today. Do you have any questions on the concepts and the ideas? Does it make sense?
Yeah, no, I think you made it make sense.
Yeah, I would recommend watching the videos just one to reinforce it and just practice a bit. It's not too bad. Like I said, the only time it sucks is when you have to do a derivative twice on something that's different, a weird looking function. Most of the time it's not that bad, but this one was just a quotient twice, so that made it long. Now, let me take roll and we'll call it a night. Where did my thing go? Here we go.